Okay, so we have finished defining what enthalpy is in terms of the first law of thermodynamics. We have also shown that enthalpy can be used as a conversion factor in lecture 10. Now we're going to see how enthalpy can be used in terms of finding out the entire heat of a reaction from the point of view of the reactants and the products themselves. I'm going to start with something known as the enthalpy of formation. All right, now, things that you're going to see in your book or textbook are symbols that look kind of like this. You're going to have your delta, H, and then you're going to have this not as a superscript. Technically speaking, the delta is a change, the same thing that I've been using as little d so far in my lecture. But this degree sign, this not, the superscript not, is what we call the standard state. The presence of that not tells you that the pressure at which the experiment is carried out is 1 atmosphere, and the temperature is 298 Kelvin. Now, this is to be contrasted with the standard states of gases, right? The standard state of an ideal gas is 273 Kelvin, but from thermodynamics, the temperature is actually 298 Kelvin. And that's because 298 Kelvin is roughly the temperature that we have on a typical summer day, something that is a lot more easy and attainable to get to by performing an experiment just in a bench top, right? Having the temperature be at 273 Kelvin, which is 0 degrees Celsius, is a little less convenient. The other thing too is that the heat is going to be given in units of kilojoules per mole. We talked a little bit about this in the last lecture, but this is something to be aware of, right? We're going to be dealing with kilojoules, not regular joules, but kilojoules per mole of a substance. Alright, so in terms of the first law, once again, the internal energy can be determined by performing a reaction at constant volume, right? If you know the heat capacity involved in the process, the heat capacity constant volume, you can find out the internal energy. Also, using the same setup, so performing the same reaction in a container where the volume can be allowed to change, can give you the amount of work that the reaction can perform as it proceeds forward. And when you subtract the work from the internal energy, you get the heat itself, which is the enthalpy, right? So technically speaking, CV times the change in temperature plus the pressure times the change in volume gives you the change in enthalpy itself. And notice right here that this is the enthalpy of formation, so I'm using subscript F to define formation. But what it really truly means is that we are producing one specific molecule. So you could think of heats of formation as combination reactions, and that's technically what these things are. You're going to start with multiple reactants and you're going to make a single product. And that amount of heat associated with making that product is what we call the enthalpy of formation. One last thing, because the enthalpy itself is derived at constant pressure, the enthalpy can be determined by the heat capacity constant pressure times the change in temperature, which once again says that the heat capacity constant pressure is greater than the heat capacity constant volume. So once again, just kind of reminding you of that. All right, so as I was stating, the heat of formation is going to be the heat associated with making a molecule from its standard elements. You're basically going to undergo a combination reaction where the reactants are the elements in their most elemental form. And whenever you look at tables of heats of formations, like the one that I'm showing here, you're going to be given values for delta H formation. You're going to have either values that are 0, negative, or even positive. Now the values that are 0, they are such because they will be associated with the element in its most elemental form. So oxygen in its most elemental state is O2 gas. And if that's what you're dealing with, the enthalpy of formation is 0 because that's the reactant. You don't make reactant from reactant. That's just, the reactant is just what it is, right? So it's the base value. But when you look at carbon monoxide, Okay, that first of all is a molecule, it's a compound, so that is not an element. This is going to have some heat associated with it. And carbon monoxide gas that can be made from carbon, graphite, and O2 gas ultimately yields negative 110.5 kilojoules of energy for every mole of CO2 gas that you make. All right. The same thing can be said about other molecules here. But here, just to give you a proper example now with CO2. If you're looking at the enthalpy of formation of CO2 gas, you are looking at an overall energy of negative 393.5 kilojoules per mole. And as far as writing an equation for this delta H formation, CO2 gas is the product, and that's the molecule that you're forming from the elements themselves, carbon and oxygen. And oxygen has to be diatomic since it's one of the Hofbrinkel elements. Now, at that point, what you need to make sure of is that the equation is balanced. But there's one specific caveat. You can only be allowed to have 1 mole of CO2 gas. All right, so the product has to be always balanced per 1 mole. And whatever needs to happen in terms of balancing coefficients for the reactants, you make it happen, right? So if you need to use fractions to make the balancing work out, then you use fractions. All right, now second thing to be said, since the enthalpy is negative, that means that you're actually losing heat. And so notice that I wrote this plus delta. The delta right here symbolizes heat. And since the heat is negative, that means that you're losing heat. And losing heat in the context of a reaction is to say that you write it on the product side, right? You're giving it away in essence. The same thing is true for gaseous water. Gaseous water is made from dihydrogen and dioxygen. Those are the elements constituting water. And once again, you make sure that you only have 1 mole of H2O, which is the product, and you use, if necessary, fractional coefficients. In the case of oxygen, 1/2, to make the balancing work on both sides of the equation. This is also negative, meaning that you are giving away heat, meaning that you're losing heat. Now, in the case of N2O4, N2O4 has a value of 9.16, and N2O4, you only want to have 1 mole of that. You need 2 nitrogens. Well, that's perfect because nitrogen is diatomic, so you have 2 of those. You want to have 4 oxygens, however, and oxygen elemental is O2, so you need to multiply that by 2 to make this work out. Since the value is positive for delta H, that means that you're actually accepting or acquiring heat. So now the delta appears on the reactant side of the reaction. And 2 extra things that I'll say, you probably remember them from former chemistry classes, but anytime that you have a negative delta H or that you're giving away heat, we call this an exothermic reaction, EXO, exo. And anytime that you have a positive delta H, or that you are gaining heat in the process of a reaction, we call this an endothermic reaction, ENDO, endothermic. Another endothermic process is actually the conversion of graphite into diamond. Diamond, yes, it's only made out of carbon, believe it or not. It's actually a non-metal. But it is a process that affects the type of bonding going on between the carbon atoms, and it is endothermic. Based on tables, you actually find out that value to be, a little bit high. It takes quite a bit of temperature and pressure just to happen. But the last thing that needs to be emphasized is that the elements in their elemental form are going to have a delta H formation of 0 because that's the base value. Everything is based on the elements reacting to give you a compound. If you start with the element in its elemental form, that's the base value, so the delta H formation is 0 automatically. Alright, so I'm going to stop right here, and we're going to, in the next video, talk about the different ways of using enthalpy to find out the heat of a reaction.